In this video, you will learn how to solve combined inequalities. Now, as we begin, there are some terms that you must know first. The first word is the word conjunction. The word conjunction in the math context means an and statement. And for an and statement, both statements must be true. Next, we have disjunction, which is an or statement. And for an or statement, only one of the statements must be true. So if I were to ask you, true or false, -5 is less than -3, and 3 is less than 5. Well, to determine this, I check each individual statement and see if we have a true or false statement. So is -5 less than -3? Well, yes, that is true. Now is 3 less than 5? Yes, that is also true. For an and statement, both need to be true, which is what we have, and so that would be a true statement. Next we have -1 is less than 2 and -1 is less than -2. The first statement is true. Second statement is not true. -1 is not less than -2. For an and statement, both need to be true. So because only one is true, this would not be a true statement because both need to be true for an and statement. So this would be false. Next we have an or statement. -6 is greater than 2 or 6 is less than -2. For this one, we just need one statement to be true. So here, -6 is greater than 2. That is a false statement. 6 is less than -2. That is also false. So because both are false, the entire thing is also false. Now if I had -6 is greater than 3 or -3 is less than 6. The first statement is false. Second statement is true. With an or statement, as long as one of them is true, the entire thing is true. So this statement would be a true statement. Now the next part is how do we graph statements like this? So for conjunctions, we graph where both statements are true. In other words, where they overlap. For disjunctions, we graph where at least one of the statements are true, which would be every possibility. So for example, let's say we had x is greater than 2 and x is less than or equal to 4. The way that I do this is with an and statement. I sketch above the actual number line first to help me visualize what I'm actually going to shade in as my final answer. So looking at x is greater than 2, we're going to have an open circle at 2, and that shades to the right. For x is less than or equal to 4, that's going to be a closed circle at 4, that's going to shade to the left. So for an and statement, we shade where they overlap. So they overlap right here in between the 2 and the 4. So my graph is going to be an open circle at the 2, closed circle at 4, and shade everything in between. So that would be my graph. Okay, now what about x is greater than 2 and x is greater than or equal to 4? So again, same concept. For x is greater than 2, it's going to be an open circle at 2 and shaded in to the right. For x is greater than or equal to 4, that's going to be a closed circle at 4 and shade to the right as well. So where did they overlap? Well, they overlap starting here, going all the way to the right. So my final graph is going to be a closed circle at 4, and then we shade into the right. Right, that's where they overlap. Okay, next we have x is less than 2 and x is less than or equal to 4. So if x is less than 2, that's going to be an open circle at 2, shading in to the left. And x is less than or equal to 4. So that's going to be a closed circle at 4 and shade to the left as well. Well, where do they overlap? Well, it starts here and goes all the way to the left. So my final graph is going to be a open circle at 2, then shade into the left. So this is my solution. And this keeps going forever, so I can draw an arrow showing that it goes forever. And lastly, if we had x is less than 2, we begin by shading or having an open circle at 2 and shading to the left. And then x is greater than or equal to 4 would be a closed circle at 4 and shade in to the right. Now this one, notice there is no overlap. So what that means is that there is no solution for that one. So there's no solution because there is no overlap, nothing that makes this statement true. So there is no graph, no solution, and using math notation, I can use a circle and put a line through it, meaning no solution. So what we've done here is we've shown all 4 possible scenarios that you might see with an AND statement. One with a greater than and less than, one with both greater than, one with both less than, and then one with a less than and a greater than. On the next slide, we're going to do the same thing, but now with OR statements. So here, if we had x is greater than 2 or x is less than or equal to 4. For an OR statement, it doesn't matter where they overlap because we're just going to shade in both answers. So this one you really don't need to do above the number line to kind of think through the process. This one you can just kind of put on the number line and do both at the same time, because that's what I'm doing. I'm putting both of these possibilities on the number line. So x is greater than 2. It's going to be an open circle at 2 and shade into the right. All right, so I have that on there. And then x is less than or equal to 4. So that's going to be a closed circle at 4 right here, then shade into the left this way. So I put both on here at the same time, draw an arrow because it keeps going forever. And notice it's going to go over top of this open circle. So you can just erase that open circle and just have this all filled in. So this one is going to be the entire number line, which means my answer is all real numbers. And the math notation for that is this fancy R. That means all real numbers. Next example is if we have both greater than. So x is greater than 2 or x is greater than or equal to 4. So greater than 2 would be here and then going to the right. All right, greater than or equal to 4 would start here at 4 and shade into the right as well. So my graph would simply be this right here. All right, and more simply put, this is just simply x is greater than 2, right? This graph is starting at 2 and going to the right. So here, the simplified answer technically would be x is greater than 2. That's the same thing as both together. Next we have both less than. So x is less than 2 would be starting here at 2 and shading into the left. All right, and then we have x is less than or equal to 4. That starts at 4, closed circle, and that shades into the left as well. When it goes to the left, it's going to go over top of that open circle, so shade that in, and you could erase that open circle if you wanted, and just shade in everything to the left right there. So notice this graph is the same thing as simply x is less than or equal to 4. So that is maybe a simplified form of the initial statement. And now lastly, if we had less than for the first one, and then greater than for the second one. So x is less than 2, we start at 2, it's open circle, that goes to the left. All right, and then from here, x is greater than or equal to 4 would be closed circle at 4 and shade into the right. All right, so keep them both on the graph, and this would be my solution. Another example, what if we had the compound inequality written like this? Now there's two ways you can think through the graph for this one. You could actually just look right here at the statement and graph directly from this, because we see x is between 1 and 5. So when I graph between 1 and 5. And they're both going to be closed circles. And that's because of this inequality here and here. See, the less than or equal to means you have a closed circle. So my graph would just be like that. All right. But why that is true is because I can break this up into two different statements. 1 is less than or equal to x, is my first statement. And the other one is x is less than or equal to 5. So I have two statements right here. In this first one, 1 is less than or equal to x, I could put the x first and the 1 after. If I do that, I would switch the inequality. So this becomes x is greater than or equal to 1. Alright, so when I graph it like this, the same way I did before, x is greater than or equal to 1 would be a closed circle at 1 going to the right. And x is less than or equal to 5 would be a closed circle at 5 and going to the left. And for an and statement, you would shade where they overlap. So notice I get the same graph. So there's a long way you can do it, or the shortcut way. So another example, if we had -2 is less than x is less than or equal to 2, doing the shortcut way, I see open circle at -2, closed circle at +2. So open circle at -2, closed circle at +2, and I shade in everything in between, because x is literally between -2 and 2. So that would be my graph. Now, if you were given a conjunction like this, if you wanted to, you could go back the other way and write this as one inequality. So to do that, remember you would take the 2 and the x. You want to switch this around, so like the 2 is on the left side and x is on this side, and then make this into a less than or equal to. I can do that because the mouth is still facing the x in both cases. Alright, and x is less than or equal to 4. So I made the sign both the same, where they're both less than or equal to. Alright, I can combine into one statement. So I take the 2 is less than or equal to x, combine that with this, x is less than or equal to 4. So starting at the x, I put a less than or equal to 4. So this would be my statement right here. So you can think of it both ways. So conjunctions you can typically write in this format. So just make sure that your inequalities are all facing the same direction. So it's both less than or both greater than. And to graph this, we just graph between 2 and 4. So between 2 and 4, just shade in right in between. Alright, and it's closed circle because of the equal sign as part of the inequality. Now, if you are given a compound inequality, you also need to make sure you know how to solve. So for example, if you had here this conjunction, it's an and statement, -1 is less than or equal to 3z plus 2 is less than or equal to 8. There's two ways you can solve this. You can keep it all as one statement and then solve like this, or break it up into two different statements and solve each one separately. So at this time I'm going to show you both, and you can choose whichever one you prefer. So the objective is always to solve for the variable, which means to isolate it and get it by itself. Which means in this case, I need to get rid of the 3 and the 2 that is with the z. So to do that, I can do inverse, or I guess reverse order of operations. So I get rid of the addition first, and I do that by subtracting. So I subtract everything by 2. So normally with an equation, you would just do the same thing to both sides, but here we have 3 sides. We have a right, middle, and a left part. So I subtract 2 from every part. That gives me a -3 on the left, 3z in the middle, and then 8 minus 2 is 6 on the right. And then to finish off, we can divide both sides by 3, or all sides, not both, all 3 sides. Divide by 3, that gives me -1, z, and 2. So this here is my solution. And I can leave it like this, or I can separate it where I have -1 is less than or equal to z, and z is less than or equal to 2. And typically speaking, you want the variable on the left side, so let's put the z on the left and the -1 on the right, and just flip the inequality so that that becomes a greater than sign. Now that is one way you could have done this problem. The other way is by separating this statement here into two different statements. Alright, so what I could have done is I could have taken this right here and written that as one statement. So I have -1 is less than or equal to 3z plus 2. And then my second statement is 3z plus 2 is less than or equal to 8. So I broke this up into two parts, and I can solve each one separately. So this first one, if I wanted to, I could put the 3z plus 2 on the left side and the -1 on the right side. Just make sure the inequality is flipped when you do that. And then to solve, I can subtract 2 to get 3z is greater than or equal to -3. Then divide by 3. So we have z is greater than or equal to -1. Now I need to do the same thing with the second equation. I solve for z by subtracting 2. So 3z is less than or equal to 6. And then divide both sides by 3 again. And now we have z is less than or equal to 2. So notice either way we get the same answer. But one way, the first way is probably quicker, whereas the second way might make more sense to you. But whichever way you prefer is totally fine as long as you get the correct answer. So this is with an and statement, and with an or statement, you just keep them separate. All right, they're not combined. You cannot solve them at the same time. So just keep them separate. And so what I can do is I can solve the first one by subtracting 7. So I subtract 7. And I get 3k is less than -6. Then divide by 3. So k is less than -2. And then the other statement, I can solve this one by adding 3. So 2k is greater than 4. And then divide by 2. We have k is greater than 2. And just don't forget your word in the middle. It's not a conjunction, but your connecting word. So make sure you write the or in between. All right, and that would be my solution. And that concludes our lesson for today. We will see you next time.